This video is dedicated to Curt Vendel, without whom this video would not have been possible, because the source code that is being generated and demonstrated in this video came directly from his archive. Hi, I'm Tom Cherryholmes, and this is another video in the Retro Computing Archaeology series. In this video, we're going to be taking a source code copy of DIGDUG for the Atari 8-bit computer. We're going to be making a single change to it, and we're going to be assembling this source code into, ultimately, a ROM image that can be put onto a cartridge PROM. There are quite a few steps in this process, and the build process is long, but the point of it here is to show exactly how this was done using the native Atari macro assembler environment. In a future video, I will actually be doing the same steps, but using the cross assembler environment that Atari used called CAMAC, which is a Data General MV8000 version of this software that ran on the big MV8000 machine that the home computer division used to develop the games. I'm in the middle of setting up that environment, so I'm not ready to show it yet, but I will be in the future. So I figured in the meantime, let's go ahead and show how this was done on the native system itself. So what are we going to be building? Well, we're going to be building essentially a prototype version of DIGDUG. This is not the release version, but it's close. It's really close. Main thing that you can see visually here on the title screen, for example, is that the scores are white instead of blue. Another thing that we'll see is that the bigars here have a different shape to them. In fact, they look like, I don't know, maybe toucans? Little toucans, I guess. Kind of funny. I'm glad that they ultimately changed them to look a bit more menacing, but you can see some of the early graphic work here. And perhaps if you're enterprising, you can take and modify that yourself now that you've got the source code. So how are we going to do that? Well, let's go ahead and peel this away. We'll take the cartridge out and we'll boot into our FujiNet environment. Build the debugger. And we can go to apps.errata.online into Atari 8-bit. And there's a folder on the second page here called source code, which is becoming a curated set of source code for all sorts of different things, such as games or versions of disk operating systems and the like. But the point is to provide disk images for interested people for study so that they can see how these things were put together in context, because the tools are also there. For example, if we go into DIGDUG here, we see that we have 4 disk images at the top, including the Atari macro assembler and the 3 disks of source code. Yes, DIGDUG needed 3 disks worth of source code. So we're looking at like almost 200K worth of source code that has to be assembled into a 16K binary. And we had to split them across and keep the macro assembler disks separate because we couldn't fit them all together. Sorry about that, but I did provide some instructions here in where to place all of these different disk images. We'll go ahead, and the thing that we need to do at this point is to copy these over to our main system using the copy function. I'll put them on my SD card, one at a time. Once we've done that, we can basically take and use them from our SD card like this. I've already done this, so I'll just skip over that. But you take and copy them over, boom. Then we can take and mount them. And since we have these all here on our own system, I'll take and go to my SD card here. Mount it, read, write. Mount it, read, write. Mount it, read, write. And finally, that copy of Atari macro assembler as well. Hold on, guys. Go for that last one there. Yeah, there we go. And I'll mount that one as read-write too, because this is my local copy. Now we have these 4 disks mounted from D1 to D4 respectively, and we're going to boot from the Atari macro assembler here. We'll go ahead and boot in. We should find ourselves, assuming we don't have BASIC in the system here, sitting at the DOS2 menu, just like this. If we take a look at what's on drive 1, we see that we have AMAC, we have a copy of emedit, which we can use to make edits to the source code, AMAC the assembler. There's a customization program if you want, so that you can take and customize your emedit environment, such as your colors, tab stops, that sort of thing, if you want to use that. Plus, I've provided copies of a few of the end utilities here, so we can take and move the resulting artifact off of our system onto our host system here, so that we can do further processing. There's also fnew and fmount, so you can do this at the disk image level if you want to do it that way too. What's on drive 2? Well, right now, that's the first disk of DIGDUG source code, with the main DIGDUG source code being right here. And you'll notice that that right there, just by itself, is 42 sectors worth of data right there. We're ultimately going to be replacing this DIGDUG object file, which is our assembled source code in Atari binary load format. What's on drive 3? More source code. And you'll see, take note of the free sectors bits right here. You'll see that we don't have that much space for a lot of this stuff. They really had to take and split this across multiple disks just to assemble. And this is how it was ordered on the build when they were working on it in the first place. So if we actually take a look, for example, at the DIGDUG source code, let's bring it into memory here using our copy command, bringing it to the screen, we can see that this is indeed the DIGDUG source code with a nice little banner at the top, some notes and some macros about assembles, but you can see various include statements that bring in the other pieces of the source code. So this particular source code, this particular file, DIGDUG.ASM, serves as a binding for all of the other bits of source code, bringing them in, assembling them into memory as it needs to. Lots and lots and lots of include files, and you'll notice that these are referenced on particular drives. Let me get back. Okay, come on, Control 1. There we go. So it goes through and includes all of the individual bits of source code here to take and build. And as an aside here, this whole assembly process on this machine takes up all of the available memory on this machine, on this 48K machine. There are exactly 102 bytes left after when the assembly process is happening. So it just barely fits inside of here. So this is why it was in everybody's best interest at Atari to use a much larger system to do the assembly. And in this case, it was the MV8000. So they took the Atari macro assembler and they ported it across. Well, finally, if we look on drive 4, the last of the source code. So yeah, groovy. So that's what we have here. We also have our little emedit here, and we're going to be using emedit to modify something in the title screen here, and something that we can see, so we can see that our changes are actually being propagated across. Okay? So let's go ahead and load emedit to do that change. That's on drive 2, it's title ASM. This was the program text editor that was used at Atari for native code development here. So we D2, and the file name is title ASM. It loads it in. Of course, we're using defaults. Okay, we have limited free space, and it's letting us know that we have limited free space, and we have just enough free space to deal with this. So let's go ahead and ignore fine. Take a moment for this to load in. And process. But once we do, we have our source code that we can pull into here. For 1, player 2. We have code here to initialize the display list. And we have count and various initialization codes. We've got initial colors. Well, as it turns out, if we look at another piece of source code here, called globals.asm, and I won't bore you with actually opening another window here, we'll go into the source code here. And we will be referencing this a bit later, but if we go into globals, we'll see that there are a number of global values for colors here, for nice names for things. We'll change the blue to, we'll change the blue here to a green. Why not, right? Okay, we do that. We come back up here, and just for the sake of messing around here so that we can show that this is happening, we'll change the DS here for the player 1 and player 2 text. Player 0 and player 1. Why not? So we go ahead, save that. We do that by pressing the Option key, which gets us into command mode. And we say exit 1, which will save the result. We press the Start key to confirm. So now we've done this. It made the replacement title ASM for us. And it actually made a backup file. So, wow, we literally ran right out of space here. We had just enough space to do that change. Let's go ahead and delete that title back. Let's make sure that it's actually okay. Oop, or not. Sorry. So you'll see, we had just enough space to do this. It made the backup file for us, and there we go, ready to go. Yay. Now we can take and build the result. To do that, we'll take and go into AMAC, and we'll load AMAC right here. AMAC greets us with its banner, and it asks us to input a source file name and options. At this point, we need to do a little bit of disk gymnastics. We need to move all the disks that were in drives 2, 3, and 4 over one slot so that everything's in drive 1, 2, and 3 appropriately. And we'll move AMAC to drive 4. Thankfully, the FujiNet tool has this wonderful little option called disk swap that will allow us to do that. If we take and hit swap here, we will see that the macro assembler is now sitting in drive 4, and D1, D1, D2, D2, D3, D3. Okay, that's all we need to do. Move that out of the way, and I can take and enter in DIGDUG.asm, and I'm going to use nothing but default options here. I'm not going to produce a listing. And the binary file is going to be called DIGDUG.OBJ by itself. We don't need to provide any systext, and we're not going to be generating a listing here. So the default options here will work just fine. We go ahead and press return to start the assembly process. This also means that DIGDUG.asm will also show up on drive 1 as well. You can hear here that it's deleting the object file, and it will reopen it. And once that happens, the assembly process will begin. So there we go. Now we are assembling all the bits and pieces for this. And for the sake of argument here, we're going to be setting a little stopwatch. My stopwatch is acting funny. There we go. We will let that happen. And yes, we're going to see exactly how long it takes to assemble this copy of DIGDUG from roughly 200K worth of source code into 16K of ROM cartridge. Once it actually gets to, gets all this read in, the general rule of thumb is that it takes, without generating any listing, it takes 1 minute per kilobyte to generate here. So we're looking at least 15 minutes for this assembly to take place. It's actually going to be a bit longer because we have to go through pass 1, which takes and grabs all the symbols and things to resolve in pass 2. So where did this bit of source code actually come from? To answer that, we need to go to Atari Age. In 2003, Curt Vendel created a little thread on Atari Age called Source Code Palooza. And Source Code Palooza was essentially him going through the 9-track tapes that were backed up from the VAX, the Atari Corp VAX. This is post-Trammell, by the way, so this was on the VAX, of various bits of Atari 8-bit source code. And this was all done back, I said 2003, I apologize, it's actually the spring of 2013. And we came across some really neat things, such as the source code for the unreleased version of Defender that Michael Colburn worked on, and the version of DIGDUG that we are currently assembling at this particular point in time. We also have right here a version of Donkey Kong that I would say is about 98% complete, a copy of Jim Heather's Football, and a copy of Sean Hannessy's Real Sports Tennis. These are all intended to be compiled with the cross AMAC that was running on the Data General MV8000 here. So what's actually in, say, DIGROM, for example, what we're actually unpacking here? There's a lot of neat stuff in here. Let's take a look. We go to our downloads and we go to DIGROM here. We'll see a whole host of files. This is the work directory. This is the entirety of the work directory, by the way. Let me see if I can zoom in just a bit. So you guys can see. You'll see the bits and pieces, these are the actual assembler files for each bit of DIGDUG here. But you'll also see files that end in BU. These are the backup files. ED, which are the editor control files. These are essentially binary state for changes and whatnot, and are specific to the screen editor that's used on the MV8000. You'll also see what's called convert ASM. This was, sorry, never mind. That's, I'll go over that later. That's for the Data General video. You'll see here a copy of what became known as Jim Dunyon's DDT, but at this time it was actually called Little Jimmy's Debugger. And you'll see various files here for assembling the content. And you'll see right here that we have a call to an assembler called CAMAC. And the parameters that you send to CAMAC are exactly the same ones that you send to AMAC, because it literally is a port of the Atari macro assembler. In our case, we've generated a listing here with the DIGDUG print, which I will take and link up so that you guys can see, and a complete cross-reference. Now, coincidentally, trying to do a complete listing with a cross-reference here will cause AMAC on a native Atari to run out of assembly space while trying to assemble this. Another one of the reasons why you used this much bigger, much faster computer to do the actual assembly work. It made good work of it, especially because you could batch process it. Just send it through and wait for the results to come back. Some of the other interesting things that happen, if we actually take a look, there is a remote batch CLI here. This is what's ultimately sent through the batch processing once the assembly is complete. And we have a little tool here called DOS-L. And this runs on the MB8000 itself. It is an implementation of the binary load function that's in DOS 2. It takes the object file that gets created by CAMAC and then creates a memory image for it to load into. Well, why is this important? Well, this is important because the result is then passed through, chopping off only the cartridge area here, making sure that it's exactly 16K, and putting the result into an Intel HEX format file. That can be sent off to the EEPROM burner. And it looks like this. So you can see it starts here at address 0 and then goes all the way down to 3FFF, which is, a 16K EEPROM. But this file right here can be directly taken and thrown into a PROM burner to take and burn the final PROM. So what they literally did, and that really kind of brings in order for me to really bring this across here, I have to take and make a small digression into CAMAC itself. And this is really amazing because what they literally did, this is the CAMAC folder that was on the MB8000, which contains everything needed to build CAMAC itself. And in the first directory is quite literally the 6502 assembler code for AMAC. This can be built with a copy of ACT on CPM or whatever to actually build, or with AMAC to build a completed copy of the assembler. And if we go into it, we can see, here it is. This is RACT, which means remote ACT. This is the assembly code translator from SourceM. And it was written by these guys originally, starting in 1979, and eventually being contracted by Atari to adapt to the Atari 8-bit to run on its things here. And what they basically did was take all of this. If you actually take and go into all of this right here, you'll see that we have equates, we have macros and things. But at the end of the day, yeah, this right here is the 8080 version of that code mixed in with some 6502 with some 8080 like macros to make sure that this gets ported well enough. So it's a little bit mixes of everything here. So yeah, they used macros and everything to take and port this over. It was ported over from 8080 into 6502, and then Atari took that and produced a version that could run on the Data General MV8000. And if you actually take and dig into that, there's a file in the CAMAC archive which describes the entire process that they went through to port that copy of AMAC that had been ported from 8080 to 6502, to take that again, that Atari version, and port it over for that could run on the MV8000. They added a whole bunch of different source code support modules. They added in routines to simulate SIO calls and CIO calls, so that AMAC could run as is on the MV8000. But the entire process is described here, what they did and the issues that they ran into, and notes about the code that you can and cannot assemble. But it was all well documented here by somebody. I would really like to know who this is, because they did an absolutely amazing job mechanically translating this code over and across. And that's what I'm going to be taking and building in a future video, essentially taking this assembler with Atari source code and running it in that environment, so you can see how it was actually done on the big systems themselves. You can compare and contrast it with the native development that is happening over here on AMAC on an Atari 8-bit. By the way, you'll notice here that we've already omitted one particular error here. This is for a particular, this error was intentional. It's just a marker, and I would like to know why these markers are actually in place. There are two of them in here, one for the startup code and the other for the ROM here. And what the assembler has actually done in this case, the assembler just continues on assembling. It doesn't stop when there's an error. What it will do instead is it will drop 3 knots into where this instruction is right here by default. That's just what it does, and then it continues on. There are 2 of these in this particular piece of code. They're not in the code path, so they don't really affect execution, and they're not really part of data. So this, I think this was actually used either as, I would speculate, either as a patch point or as a hook for DDT, running it inside of DDT. If anybody really has an idea, if anybody wants to investigate, this would be something really worth investigating here. We should be nearing the last leg of our assembly here, by the way. One of the nice things that you can do with your FujiNet also, by the way, if you want to take and build a listing, well, you can, and your printouts will look absolutely gorgeous. For example here, this is from the Atari 825 with page site set appropriately here. And we can see all of our where things are being assembled. In this case, for the DSs, the amount of space that they're being taken up, etc., etc. You can see all the bytes that are being assembled into memory. Looking great, you know? The FujiNet allows you to get these nice listings from these assemblers and just do a bang-up job of doing it. So if you want that, I've provided a link to this in the video description, so you can take and grab a copy of this yourself, so you can take a look and follow along if you wish. All right. And yes, it really did take this long to assemble a full game on native hardware like this. So every bit of coding time counted. You really wanted to get your bugs out before you hit your assembly, because your turnaround times would get longer and longer. If you haven't, I would suggest grabbing a copy of Atari Inc. Business is Fun. That was the book that Curt Vendel and Marty Goldberg worked on. They were actually planning a follow-up called Atari Corp. Business is War. Unfortunately, Curt died before the initial research could be completed. I don't know how much of that research was actually completed. I don't know how much of the book was actually written, but all of that stopped, unfortunately. It would have been an interesting counterpoint and contrast against Atari during the pre-Warner and Warner days against the Trammell days, which were decidedly a very different corporate culture. I'm just going to let it sit here until the assemble completes. And look at that. Okay, it is now complete, and we're at about, I'm going to say 18 minutes to take and compile that entire chunk of DigDug here. That's it. Now the object file's created. Now take a look at this right here. There are less than 256 bytes of RAM free for this assembly here, so we were really cutting it close. And turning on the listing and the cross-referencing options really cuts that down even further. So with this, we're actually pretty much done with this leg of it here, and I will take and cold reset my system here, which will also reset my FujiNet so we can go back in. And we can boot again to see the results. Now again, I reset my FujiNet, which also reset the disk swapping, so everything is in as we put it in at the first of the video. So that means that AMAC is in drive 1, and our D1, our source code in D1 is in D2, but now we actually have our DIGDUG object here. We have our finished object code. Can we load it? Well, yes, but you're going to see something rather interesting that happens as a result of doing this. If we take and load the object code as it is right now, it will indeed load. But we're going to have some issues. The first is Well, we can see our change that we did here. But there are some improperly initialized bits of RAM here. You can see that our score counter is all messed up, but you can see our changes here. So the change was successful, and it's okay. And what you're going to find, and I'm going to demonstrate this by going into the debugger. I will take and pop the debugger, pull a window for a console here real quick, and I will show you what's going on. I'm going to show you a particular memory address, 9849. This is within the cartridge ROM area right here. Except there's no ROM here right now. This is all RAM, and we've loaded a ROM into it. So that means if you've got code that is like copy protection that tries to take and write to this area, this is RAM, so that'll actually succeed. And in this case, it's actually going to crash the game. But we can see that our objects are okay. If we start, we immediately see that now we've hit an illegal instruction at 9849 here. 02 kill. It's a deliberate instruction here. So now if I look and compare what has happened here, it's the same damn thing, except we have changed 1 byte. We wrote 1 byte here to be our kill instruction. And it has unfortunately thrown everything into upheaval here. So we can't test like this directly, except if we take and load our debugger. And I will take and do that in a future video because I am still reverse engineering how the debugging environment was completely set up. There are some special things going on there. So what we actually have to do now is we have to take and build a ROM image. How do we do that? Well, first thing we need to do, we need to get our artifact off of our Atari and onto our host machine. In our case here, we will take and use the FujiNet tools to accomplish this. This would be accomplished using a modem program, using a serial connection, something just to get our data off. As a subject for yet another video. But let's go ahead and load our, do that again. Let's see. Atari macro assembler. And do a read write. And drive 1 here. Read write. And boot. Now we have this. Okay, great. We have our object in drive 2, and we're going to use the ncopy command to move that over. Recall the ncopies on drive 1, and we're going to take and pull that across. This is a modern step, but I'm doing this to get to move us to the finish line here. So I'm going to move this to my file server here. D2, sorry. Now, ironically, one of the things that we could use here that I don't have emulated would be to use a pill-like device. Load the binary into memory, and then when the game starts, flip the pill device on to basically take and write protect the RAM area for the ROM so that the copy protection measure that's here in DIGDUG won't fire off and the game will play correctly. I don't have a pill here with me. Okay, now that's in place. That's now copied. We can now take and pull this out of the way for just a moment. We will go to another, I'm going to open up another window here. And we're going to look at what we have here. Let's take some preferences. Let me take and do a little bit of finagling with the text size here. I will pause the video while I do this. Also got the stopwatch out of the way here because we're done with that. Okay, guys, what do you think? Okay. Well, recall that we had a little tool called DOS-L, which whole purpose was to take and load that binary load file into place. We're going to be taking and implementing that tool so you can see what that tool actually did and why it actually did. So, all we really have to do, I'm going to use a little tool. And we're going to go look in, sorry, TNFS, my TNFS server here, and we'll see our DIGDUG.OBJ file. There it is, ready to go. It's been copied over, and you can see, yeah, this is the file that got copied over here. I'm going to use a little tool called XEX filter here to show you how AMAC built the object here. Now, AMAC has this habit of building things in 252 byte segments. So you see we have a lot of stuff that has kind of just peeled away over here, right? All these little segments, and it all peels it together. And we have a run address here that goes to our initialization routine, okay? Well, since Atari ported AMAC as is, this behavior was replicated. So the tools guys had to take and make a complete implementation of the binary load routine that would load into a memory image that they could then further process. Well, what is that program? It turns out there's really not much to it. So if we go ahead, I'll make a little space for it right here in DOS-L. DOS-L.C. And what is this thing? Well, I'm just going to pick a language to take and implement this in, and I'll use C here. And there's not much to it. And standard IO, standard lib, and string. Nice and easy. We're also going to be taking and loading this file into a virtual chunk of memory. That is 65536 bytes long, or the 64K address space of a 6502. Okay, put that right there, ready to go. And this program, ironically, it doesn't need any parameters, but I'm going to go ahead and put them in here anyway, because it's just standard. And the way that this program is going to work, it is going to read from standard in, and it's going to spit out the memory image to standard out. So you can put this in a pipe. So, unsigned care. Binary files begin with 2 binary header bytes. FF. So we just go ahead and grab them. And we check for a header. And if that header is not FF, and FF2 is not FF, then we say, okay, we spit out an error message. And we indicate that we're exiting. And we put that in standard error so that we don't cloud up our pipe. Log up our pipe. Yeah. Lovely metaphor there. Okay. At that point, okay, this is a binary file, so we just read and process chunks. Atari binary files are pretty simple. Once you figure out that you've got a binary load file here, you've got each chunk has a 4-byte header, which says, okay, start from this address to this address. And it's inclusive, so the length is end minus start plus 1, okay? So all we really have to do at this point, FEOF standard in, bam, okay, unsigned short, start, unsigned short, end. You add 2 addresses and a size derived from both. Those are the 3 variables that we need for each chunk that we're going to deal with. And all we have to do, check this out. So all we really have to do is get the start and end addresses, which are unsigned short, one of those, grab it from standard in. Same thing for the end addresses. Learn to type there, Tom. And then we calculate the size as end minus start. You might say end minus start. Well, wait a minute. Turns out it's inclusive, so we need to also take and add +1 here so that we get the correct length. So at that point, we have our start and our end, and we have our size. So all we have to do to put this in our memory image is say, okay, I want to read here at memory, starting at this offset right here, size number of bytes, do it once, and do that from standard in. That gets it into our memory image. And that loop runs for as many chunks as you have inside of your memory image. Done, done, and done. At this point, you can take and then output the resulting memory image. So we grab mem, size of mem, and then there's only one of those, so standard out. We spit that up to standard out. And that's all we have to do. At this point, we just return 0 and Bob's your uncle, right? Boom. So we compile that. Looks good. Now all we have to do to use it, we'll just take and pull it into our utility space so we can use it. Done and done and done. Okay, great. So there is that. Now we go back to our download, back to our TNFS server where we have our little deal here. Okay. And at this point, we can then take and echo our DIGDUG.XEX here. And we can pull that into DOS-L and then output the result as a DIGDUG memory image. Or not. Hold on a second. Oh, sorry, not echo. The file, it's working exactly as it's supposed to here. So we see our error. Okay, fine. Cat DIGDUG.XEX DOS-L DIGDUG.MI. Now, what did we just take and put into place here? We now have a memory image of that DIGDUG file loaded into a nice 64K space. Okay. If we do a hex edit on it, we can take a look at it and see what we have to work with here. You're going to find the majority of that 64K memory space is empty, save for 2E0 and 2E1, which recall, we had a binary segment that loaded right there, and that's the start address. We don't need that, but our loader took and did the right thing and put it there anyway. Okay? That's fine. So we scoot all the way down until we hit 8,000, at which point there's our cartridge. Our cartridge now starts, and all the little bits of binary data load all the way in until we hit BFFF, the end of the cartridge. And you'll see the EA for the end ROM error that happened right there. There's one of these at the start of the ROM, and there's one of these at the end of the ROM here. So I guess he's using it as a marker. But you can see the cartridge header here with the start address. and the cartridge type, and initialization addresses. Good to go. This looks like a sane cartridge. So now all we have to do, we can take that and turn that directly into a ROM image. Okay. Give me just a moment here. Sorry, I wanted to try something to see if DD could actually handle hex numbers. It doesn't. Too bad. That's okay. All you have to do is do a little bit of do a little work on the calculator here. Sure, 32,768 bytes. So what we need to do is we need to take our memory image that we've done here, and we need to output it to a ROM file. We're going to skip the first 32K of memory. We don't need it. The cartridge starts immediately at the 32K boundary, and we're working in byte-sized pieces here, 1 byte per byte size, and we're going to say count 16384 because this is a 16K cartridge. This is equivalent to that what I showed you earlier here. It's taking this and building out that 16K ROM image because everything is needed is in the memory space. The loader took care of putting it all in, including the cartridge footer and everything else. So we take and have a nice 16K ROM that we can subsequently take and run. We can run it correctly. So if I now take and boot that image, that DIGDUG.ROM image, by the way, DIGDUG.ROM, DIGDUG.ROM, 16K. There's our cartridge with memory properly initialized, everything good. And the game starts. There you go. And it's working. Now the additional step here is converting this into Intel HEX so you can send it off to the PROMers. And in our case, we can use object copy for that. And we set an input type, input target of binary, and an output target of HEX. There's our Intel HEX file, say DIGDUG. Our input file is this. Our output file is this. So if we now take a look at DIGDUG.HEX, we now have our Intel HEX file that we can take and send right off to the PROMers. So there we go. We'll go ahead and pretty much end this video right here at this particular point. So we've taken the whole process of taking a modification, assembling that modification, taking and loading that into a memory image, and then taking and building a ROM from that memory image by only selecting the part of that memory image that we need for the cartridge to function. A future video, as I said before, will actually repeat this process on CAMAC itself, using the tools that are on there so that you can see how this was done at Atari in the home computer division. Hopefully I can get all of this working because I do have a working emulation environment that sufficiently works well enough that I can start an MV AOSVS environment and use that to actually run the assembler. If any of you are well versed enough in operating an AOS environment on a data general system, I could really use your input to take and make tapes so I can move everything across, because that's literally what I am trying to figure out at this particular point in time. But as you can see, we have an AOS system that's running. It is just completely and utterly blank. there we go. With that, we'll take and finish up where we're off here. And I will we'll pick this video series up when I have the next piece ready. So until next time, guys, have fun.